Hello everyone, welcome to this lecture on electromagnetic induction. In today's lecture, we will talk little more about displacement current, considering the capacitor example, and we will also discuss continuity equation. So this is your syllabus structure, and we have almost covered all the topics that has been given in your syllabus. So in the last lecture, we talked about the displacement current and its origin. We learned that there is an inconsistency in the Ampere-Circuital law, and by divergence operation, we could prove that there is an inconsistency in the Ampere-Circuital law, and ultimately Maxwell came into the rescue of it, and he found out a way to make the Ampere-Circuital law complete. Now, that was a mathematical operation. What about the physical example? Do we have an example of physical existence where we can prove that yes, Ampere-Circuital law is having some kind of an inconsistency? The answer is yes. So let us consider the capacitor example. Simple, there is a capacitor and there is a battery. When the battery is being connected across the capacitor will charge. So in this example, you can see in this diagram, there is a battery. This is the positive terminal of the battery. This is negative terminal. So when the positive terminal is connected to this plate will acquire positive charges. And since the negative terminal is connected to this plate will acquire negative charges. Now, the charging will occur until and unless there is a potential difference V across this capacitor, which is exactly equal to the potential difference of the battery. So whenever the potential difference of the battery and the capacitor becomes equal, in that case, the charging process will be stopped. Now, let's see how exactly we can apply the Ampere-Circuital law in this case. Now, Ampere-Circuital law is given by the line integral, by the closed loop line integral of the magnetic field, that's equal to mu naught I. Now, what is this I? This I is the current enclosed by the loop. So, if I have got an Amperian loop, say this is an Amperian loop through which there is a current passing out, piercing through this plane of this paper. In that case, I will say that there is only single current lead which is being captured or which is being considered under this Amperian loop, and there will be mu naught I. Suppose there are two current loops. In that case, it will be mu naught, say I1 plus I2. That means there are two currents and we have to sum them up. Now, how would we know that the current must be considered under the Amperian loop? For this task, we construct or we put an I on this surface. Now, since these current leads are piercing through this Amperian surface, that is the reason why we are considering this current. So, in this case, in this example, the current direction is given by these arrow marks. So, let's consider this particular surface. Now, this is my Amperian loop, which is being bounded or which is bounding this current lead, and corresponding to this loop we can think of two different surfaces. One is this balloon shaped surface and second one is this open surface. Now when we consider this open surface, we can very clearly see that the current lead is getting pierced through this particular surface. So that is why when we apply Ampere-Circuital law, we can get easily that B dot dl integration taken over this closed loop is given by mu naught I. But what about this particular surface, that means the balloon shaped surface? If we consider the balloon shaped surface in such a way that it goes through in between region of the two capacitors and doesn't touch any of the current loop or the capacitor plate, in that case, essentially this particular surface does not allow any current lead to pierce through it. That means it never goes across the surface. But this is also a surface which is holding up this Amperian loop. Now in this case, if I apply Ampere-Circuital law, then I am going to get B dot dl to be equal to 0. Why? Because there is no current which is passing across this particular surface. Now here you see we have considered the same current loop, we have considered the same Amperian loop, but even then the Ampere-Circuital law in one surface was giving a different result, and for the different another surface it is giving a different result. So that means what? There is a sort of discontinuity or there is a sort of inconsistency with the Amperian loop. So I have considered the single Amperian loop, but corresponding to single Amperian loop I can construct many different surfaces. So many different kinds of surfaces may have the same loop. So in this case, I can see if we consider the open surface loop, which is holding up the current or which is allowing the current lead to pierce through it. In that case, it was giving us a value mu naught I. But whenever I considered a pot shaped surface or the balloon shaped surface through which the current lead was not piercing through, in that case, it was not holding up a current. So same Ampere circuital law was behaving in a two different fashion corresponding to the surface of consideration corresponding to the Amperian loop. So that is why that Ampere circuital law is behaving in different fashion. Hence, it itself shows that Ampere circuital law is, sort of inconsistent. Now, if I consider the Maxwell's modified version of Ampere circuital law, in that case, let me just rub this particular slide. What Maxwell gave us? Maxwell gave us that there is a term which is like del cross B, that's equal to mu naught J. This J is the actual current plus mu naught epsilon naught del E del T. So this is the electric field variation with time. Now in this case, you see whenever both these plates were being charged, initially suppose at time t equal to 0, there is one charge coming over here, there is a negative charge coming over here. Then the next time instance, there may be two charges coming over here. Similarly, two negative charges will come over here. So resulting what? The electric field which will be there in between these two plates, that electric field will change with respect to time. That means you will get del E del T term, which will be not equal to 0. That means there will be a definite value of the variation of the electric field with time in between the charged capacitor plates. So when you consider this particular surface, the balloon shaped surface, in that case, although the real current was not giving you any kind of a value or magnetic field, but the variation of the electric field with time will certainly give you the value of this curl of magnetic field. So that is why the curl of magnetic field is not only because of the real current which is being flown, but it is also because of the variation of the electric field with time. Got it? So when real current was not piercing through the surface, in that case, you are getting the magnetic field from the time variation of the electric field. So that is the reason why the Maxwell's modified version of Ampere circuital law is the most consistent, or rather the consistent one. So without this displacement current part, Ampere circuital law could never have been consistent one and could never have been a complete one. So now this particular thing is complete and it can justify any situation given. All right. So this is a very physical example, not mathematical one, of charging of a capacitor plates, where we can see that displacement current, or we can see the significance of the displacement current. All right. So please go through this slide and try to understand. If you have any doubt, in that case, please make a question. We will try to understand together. Right. Now let's come to another very important equation, that is called continuity equation. Now continuity in physics means what? So a continuity equation in physics is an equation that describes the transport of some quantity. So continuity equation, it could be mass transport, it could be charge transport. So in this case, we are concerned with the charge transport, not the mass transport. So what we know, that flow of charge per unit time is called current. That means current is basically given by charge per unit time. That is a very crude definition of the current. Now again, the flow of charge per unit time, per unit area, is known as the flux. Normally flux definition gives you like anything per unit area per unit time is known as the flux of that particular quantity. So if you talk about the charges, then charge per unit area per unit time will be the flux of charges. So basically if you just take charge per unit time together, in that case you can write the flux to be equal to I upon A. So this quantity, which is actually nothing but the flux of charges, is defined as the current density J. Alright, it is defined as the current per unit area through a surface. Now, continuity equation says in a volume tau, let's consider the volume tau. Why I'm writing tau actually? Because in electrostatics or electricity, V normally designate for the electric potential. So that is why for volume I'm not writing it as V, I'm writing it as tau. So if within a volume tau, if there is a divergence of the current density J, means suppose you have constructed a volume, just think of a volume, it could be cubical volume or volume of any particular shape. If there is a term del dot J, which is a positive term, if you find this term to be non-zero within a volume, then that itself means that within the volume, then it implies that the charges are flowing out through the volume. That means if there is a flowing out of charge out of this volume, then only there is a positive divergence of the current density within that volume. So that is what actually is the meaning of continuity equation. So why there is a negative sign? The negative sign shows that there is a decrement of charges within that volume. So thus the negative rate of change of charges or negative rate of flow of charges in a volume is equal to the divergence of this current density parameter. Alright, so in short, how can you write mathematically that del dot J, which gives you the divergence of J, that's equal to minus del rho del T, where rho is the volume density of charges. Alright, and if you just take it to the left hand side and write them together, then you will write it as del dot J plus del rho del T. So this equation is actually known as the equation of continuity. Okay, so this is blindly we have applied in one of our lectures when we were talking about the removal of inconsistency from the Ampere circuital law as Maxwell did it. So now we understand how exactly this continuity equation appears. This continuity equation appears from the flow of charges out of a closed volume. So if you find a divergence term which is positive within a volume, then there must be associated flow of charge out of that particular volume. So they combining these two facts, we get or we can construct the continuity equation. So this particular slide gives you us a brief idea about how exactly this thing can be derived out. So how exactly we can derive the continuity equation? See, mathematically, current is nothing but suppose there is a volume through which charges are flowing out. That means what? There is a negative rate of charge, negative rate of charge flow. That means ddt of q will be negative. So the negative sign appears because the charges decreases within the volume due to outflow. Now if dq charge is enclosed in a volume, let's in this particular volume there is a small amount of charge dq, and let's consider this volume element be designated by d tau and leaving the surface area ds. That means the whole surface of this volume is given by ds. Then what you can write? You can write the current to be is equal to integration j dot ds and q to be is equal to rho d tau. Alright. Now if you just put these two facts in this particular equation, then you are going to get on the left hand side there is a current I. So instead of writing this current I, you are writing that integration j dot ds and ddt of rho dv. There is a negative sign which is of course there. Now we know that whenever we have to take this ddt term within this integral version, integral sign, then it goes as a partial derivative. So you get j dot ds that's equal to minus del rho del t d tau. Now this is a surface integral, this is a volume integral. I cannot equate them or I cannot take the integrands out. So what I have to do, I have to convert the surface integral into volume integral, and we know how to do that by using Gauss divergence theorem. So by applying Gauss divergence theorem, we have simply converted into volume integral, just took the divergence of j, and now since I have volume integral on both the sides of this equation, I can equate these integrands. So I get del dot j equal to minus del rho del t. Alright, so this is how we get the equation of continuity. Alright, so that's all basically I had in this lecture. Please visit this particular lecture, please go through it. This is a very small lecture and sort of an extension of the previous class that we have done on Maxwell's equation and displacement current. But this is a very significant one because we have understood a physical example where the displacement current is important. Alright, please go through this. Thank you.